Okay, we've a worked example here. This is another one for transformation of graphs, and this is the so-called R formula. It's not a term I really like because it doesn't really give an idea of what this is about, which is about transformation of graphs. And in this case, it's based on the trigonometry. So let's have a look. So we've got express 5 cos x minus 3 sine x in the form r cos x plus alpha. R is greater than 0, and alpha is between 0 and half pi. Okay, so let's just read through the whole question. Hence or otherwise solve the equation 5 cos x minus 3 sine x equals 4 for this range. Well, to be honest, solving this equation like that is going to be a little bit tricky. So what we note with this is that basically the linear sum of sines and cosines, well, if we draw this function 5 cos x minus 3 sine x, this is using Desmos, then we get this. And what is this? Well, basically it's a sine curve, isn't it? We could also say it's a cosine curve. Let's say sine curve for the sake of argument. But in fact, let's say cosine, because that's what this question is. So it's a cosine curve, but it's not. It doesn't kind of start at 1, does it? And it doesn't have a full cycle of 2 pi, which is about 6. No, indeed, it's not. It's actually shifted. So the highest point is to the right. And the amplitude is, well, it's nearly minus 6 to plus 6, isn't it? So now, so it turns out actually that we can represent a linear sum of sines and cosines as a cosine, a shifted and stretched cosine, or a shifted and stretched sine, depending which we choose. We're choosing to do cosine here. Okay, so this question really is about how we actually do that. So what we do, let's have a look at our trig identity here. So yeah, this is the cosine of a plus b, and we've got this identity where this is identical to cosine of a cosine of b minus the sine a of sine b, and we're going to use that fact in this problem. So if we actually kind of use this but adapt it for r cos x plus alpha and expand that using our identity, then basically this is what we get: r cos x cos alpha minus r sine x sine alpha. Now what we're trying to do is we're trying to represent this. So if we do a bit of comparing of coefficients, first of all, the coefficient of cosine of x, these two are constants here, the r and the cos alpha, and therefore they we can equate them to 5. Our cos alpha equals 5, and likewise we've got minus r sine alpha is the coefficient of sine x, and that is therefore 3. Okay, so we've got r sine alpha equals 3, r cos alpha equals 5, and that gives us tan alpha is 3/5. And then if we just take the arctan, then we're going to find that alpha is therefore 0.54 radians. Okay, that's good. So we've got that bit of our cos x plus alpha. What about the r? Okay, for this one, we're going to use this identity. And if we square this and square that, we're basically going to get r squared alpha all squared plus r cos alpha all squared is going to be equal to this 3 squared plus 5 squared. Factorize out r squared, and then of course this term is equal to 1. It's 34, so r squared is 34, and r is square root of 34. So we've got the r and the alpha. That's great. So now we can say that our original function here, we could write it as the square root. Oh, so the square root of 34 cos x minus 0.54, and that's in radians. So now, if so, I told you this graph here is the graph of 5 cos x minus 3 sine x. Indeed, it is. But were I to draw this function, square root of 34 cos x minus 0.54, I would indeed get the same thing, which is the whole point. And when we look at that, of course, the root 34, which is just short of 6, isn't it? That's the stretch. But that's about right, isn't it? Look, yeah, it's just the amplitude, the highest point there is just short of 6. And the shift is 0.54. That's radians. These are all radians along here. And there we go. It's about half, isn't it? So yeah. So that actually is the same curve. So that proves our point, really. Okay. So that is part A. Right. Let's just roll down to part B. Okay, so we want to solve this. So we can solve this by using our alternative form, our root 34 cos x minus 0.54 equals 4. And just squeeze back up to the graph here. What we're looking at are the points of intersection with this yellow line. So this is the line. It's 4, y equals 4. Function is equal to 4. So so we're looking for the intersection of this curve and this line. So we're going to solve this equation in order to do that. So basically, we just go through these various steps. So if we divide through by root 34, which is equal to that. Then we take the arc cos and we actually solve for this angle here. And we get these values here. Well, I've taken these 3 values. This is the first negative one here. This is 0.815 here. And this is the higher value up here. Okay, so but that's x minus 0.54. We evaluated 2 pi minus 0.815 there. And then therefore x is going to be these values here. So I just added 0.54 into each of these. Now this one's out of range. It often serves to just do something a little bit wider than your range event, then throw away some solutions if they don't fit into the range that you require, as this one doesn't do. But just to check, that 0.275 is here. Again, that looks about right, doesn't it? 1.345, yeah, that looks around about right. And this is your 6.008 there again. It's about right. So what have we got? We've got these two solutions, 1.345 and 6.008 to 3 decimal places, and those are the 2 solutions in the range 0 to 2 pi. That solution. So that's it basically. So yeah, so just as by way of a recap, we've actually used our trig identity here. And compared coefficients. We can resolve. It's sort of simultaneous equations problem, isn't it? Really. So we resolved to find r and alpha, and then we've used our identity in order to solve this equation, because it's a lot easier with just one trig function in than trying to solve this. It's got 2 different trig functions. We could do it, but it would be more difficult. So that basically is it. So thanks for listening.